Okay, well, welcome everyone. Good evening. Glad you could make it out. I'm glad it's happening tonight, not last night. Uh, but I would have been, yeah. Be like Newton giving an empty lecture. So good job, Astros. I just got to get that out there. So if you're joining us online as well, thank you for being here. If you're in LA, I'm sorry. But tonight I'll make up for that. Sorry, Bob. Yeah, I know. Yeah. Just I heard it just now. Yeah. Okay. All right. So this is the second presentation in our current series, looking at ocean worlds and the outer solar system, diving into ocean worlds. Our first presentation last month was from Dr. Paul Shank here at LPI, and gave us like an overview of the Voyager missions and what they taught us about ocean worlds, or the fact that we learned we had them other than Earth in the outer solar system from Voyager. Tonight we're going to hear about more specifically about one of those ocean worlds, Europa. And in January, our next talk, January 11th, is with Dr. Jonathan Lunine from Cornell University talking about Enceladus. So that should be good. And he sent me the title for his talk at about 2 o'clock this afternoon after I'd printed the flyers. So the flyers just say Enceladus. It looks like it'll be a very, very interesting talk, though, based on that title. It was a long title, so I didn't write it down. And I want to let you know about, I don't have flyers for it, unfortunately, because we just got confirmation today on this. But December 2nd is it Saturday. We are going to have kind of a two-part public event that afternoon, that evening, for the Apollo 17 45th anniversary. And Dr. Harrison Schmitt will be here, part of the event that afternoon, and then giving a presentation like this evening's that night at 7:30. For those of you who are younger than me, Harrison Schmitt was the only geologist to walk on the moon during the Apollo missions. We will be instituting a ticketing system for that. We did this a few years ago with that movie series we had because of its popularity. It's pretty simple. You will register online through our website, and you'll get a little ticket through your email, and just bring that with you, and we'll have everybody's name when you get here. Because we have this room in our overflow, but we anticipate this could be much bigger than what we can hold. So we will be doing that. We'll send out information about that in a couple of weeks. And we'll open that up a few weeks before the event. But I wanted to get that out there so you all could at least be aware of it. December 2nd. The afternoon activity will be from 4 to 6. The library will also be having an open house during that time. So if you've never been here, because you always come here after hours and haven't been able to go to the library, you'll have that chance that day as well. And then the presentation that evening will be at 7:30, just like these. So if you are not on our email list and want to make sure you find out when that registration will open, sign up at the table to the left, or when you're walking out to the right of the doors, put your email there and make sure you get on our list. Teachers, if you're here, welcome. We got PD certificates for you at the front desk, so grab one of those before you go. And of course, we'll have a reception in the lobby that will follow, as we always do. So now I'd like to invite Dr. Louise Proctor, the LPI director, to come up and introduce tonight's speaker.
All right. Thank you very much. Okay, so for the last 2 days, we've been holding a workshop here at the LPI. We've had almost 50 scientists in the building discussing what we think is going on inside the ice shell of Jupiter's moon, Europa. It's one of the most fascinating places in the solar system, we think, and it's the topic of tonight's lecture. I can't say we figured it out, but it's been a lot of fun trying. And it's my great pleasure to introduce one of the most eminent of the scientists that has been here. This is Dr. Robert Pappalardo, who's going to speak to us tonight. In 1986, Bob received his Bachelor of Arts degree in Geological Sciences from Cornell University, where one of his professors, I think inspirations, was the late, great Carl Sagan. And in 1994, Bob obtained his PhD in geology from Arizona State University. From there, he moved to Brown University, where he became a postdoctoral researcher, and he started working on the Galileo mission which was in orbit around Jupiter. And I know some of you in the audience probably worked on that mission. I think we've discussed that before. And he was an affiliate member of the Galileo imaging team. And during that time, he worked to plan many of the Galileo observations of Jupiter's icy Galilean satellites. And that's actually where I met Bob. I was a graduate student at that time. And we became friends and collaborators. We've been collaborating for over 20 years. And I think it's no underestimate to say that Bob's become one of my most important scientific mentors during this time. After leaving Brown, Bob became an assistant professor of planetary sciences at the University of Colorado at Boulder, and he stayed there until 2006. And at that time, he joined the Jet Propulsion Lab in Pasadena, California, where he first became the project scientist for the Cassini mission, which of course just ended, sadly. It was a wonderful mission. And he is currently the project scientist for NASA's new mission to Europa, which he will tell us about tonight. Bob's research focuses on processes that have shaped the icy satellites of the outer solar system, especially Europa, and the role of its probable subsurface ocean. So please join me in welcoming Dr. Bob Pappalardo.
Really appreciate it. I'm here to talk with you about Europa, one of the most fascinating moons of the solar system. And, oh yeah, I don't have my lavalier mic on. That's the problem. Yes. There we go. Ah, that's better. I want to talk with you about Europa, one of the most fascinating moons in the solar system. You'll see why. Because this ocean world has the chance to support life. So it's fascinating geologically and geophysically, but why does most of the public care and why does NASA care? Because Europa has a chance to support life. And it's not exactly, let's see, the kind of life we're talking about is not not little green men. By the way, so I'm originally from New York, so yeah. Besides, no, don't worry. I hated the Yankees. Don't worry. I hated them as much as you did. That's not a problem. Well, exactly. So it's really hard living in LA because you hate the Dodgers because they left. But what can you do? So Houston was the better team. There was no doubt in this series. So we're not looking for this guy exactly, but to understand whether there could be microbial life at Europa. Right? We're talking single-celled organisms. Why? Because people, or that green thing that we imagine, need a lot of energy to survive. A place like Europa is probably rather low in energy. We'll talk about that, but it might have enough to support life. When we talk about searching for life, doing that really means going to the surface of a place like Europa and scooping up some stuff and looking at it in a microscope and putting it in a mass spectrometer. That's not what we plan to do as our first mission. What we plan to do is a mission that's a multiple flyby of Europa. From orbit about Jupiter, we're going to fly by Europa many, many times, a couple of dozen times at least, a few dozen times at least, and get the first really close-up, really global data set of Europa, because we're trying to understand, is it a habitable environment? That's the first step. We want to understand, are there the planetary ingredients for life? Water, the right elements to build organic molecules, chemical energy. So that essentially means, do the energy sources exist for chemical reactions to take place that could support life? And is it a stable environment, one that's probably been around a long time, as we think it probably has been. So parallel to the exploration of Mars, first we want to understand Europa globally, understand, is it a potentially habitable environment, and then with a future mission, we can go down and literally search for life, go for the brass ring. So I'm going to talk to you a bit about what makes Europa fascinating, why we think there's probably an ocean within, and how we intend to go explore it. So first, some context. One of the first images of Europa. So over 400 years ago, Galileo Galilei first turned his primitive spyglass to the heavens and saw that Jupiter had these four little, what he thought were stars next to it. And then he realized night after night, observing that these apparent stars were actually going around Jupiter. And that revolutionized our understanding of our place in the universe, because there was this idea from Copernicus that maybe the Earth was not the center of the universe. Maybe instead, Earth went around the sun, and our moon went around the Earth, and that was a pretty revolutionary idea. And by seeing that Jupiter was a center of motion with these moons going around it, that led to the Copernican revolution and changed our sense of place in the universe. The Earth was not the center of the universe after all. This is what we know of those four largest moons of Jupiter, the Galilean satellites, named for Galileo Galilei: Io, Europa, Ganymede, and Callisto. Ganymede and Callisto are kind of half ice and half rock. Io is the most volcanically active body in the solar system, all rock, and iron down below. Europa is probably mostly a rocky object with a thin skin of water and ice, as we'll talk about. And a real hero of our story is the Galileo spacecraft, as Louise mentioned, which orbited Jupiter from 1995 to 2003 and made about a dozen flybys of Europa. And most of what we know about Europa is from that mission. Europa's surface looks a lot different than, say, our moon, which is, of course, covered with craters. Here you see this one, about 20 kilometers in size, Pwyll, or Puch, if you're Welsh. I don't quite say it right. But there are not many. Well, here's one more. So actually, by the paucity of craters, we can estimate the age of Europa's surface as about 60 million years old. That sounds like a long time, but that's only about 1% of the age of the solar system. So the moon, Europa, has been around the whole age of the solar system, but something has repaved its surface over the last 60 million years or so, since the time dinosaurs roamed the Earth. This is what Europa looks like close up. It's this bright stuff is ridge plains consisting of crisscrossing ridges and grooves, and the darker stuff is, a lot of it is made up of this chaotic terrain that kind of looks like that older ridge plains has just been fried on a grill or something. And we'll talk about what might make these features. This is what we think we know about the interior of Europa. It probably has an iron core down at the center. It probably has a rocky mantle, which makes up most of the moon. And then this outer skin, about 100 kilometers thick, exaggerated here a little bit so you can see it, of H2O. And the surface of Europa is so cold, 100 degrees Kelvin, that there has to be ice at the surface, ice that's so cold that it acts like rock. And the question is, how much, if any, is liquid water below? That first, most important, really, ingredient for life. In fact, if we're right and we think there's probably about 80 kilometers or so, or 100 kilometers worth of liquid water down there, then Europa has more water within it than all of Earth's oceans combined. So how do we really know what Europa's interior is like? Well, one way is from gravity. By flying by the moon, we can get an idea of how centrally concentrated the moon is. That's why we know there's an iron core, or probably an iron core, and this outer lower density layer that's probably H2O. But how do we know it's liquid? Well, the most important way, I'm a geologist by training, and you'll see a lot of geological evidence for an ocean, but that's very indirect. The most direct evidence is from Europa's magnetic field. And that magnetic field is probably not intrinsic to Europa. Instead, it's because Europa is moving through the gigundous magnetic field of Jupiter. And in moving through Jupiter's magnetic field, from Europa's perspective, Jupiter's magnetic field is changing as Europa orbits. Because, well, I won't go into too much detail, but because Jupiter is rotating and that magnetic field is tilted, the effect at Europa is the magnetic field changes as Europa minds its business and orbits around Jupiter. And what the Galileo spacecraft did as it flew by is it noticed some unusual signals as it flew by Europa. There were blips as if Europa does have its own magnetic field, but then when Europa was in a different part of Jupiter's magnetic field, the signature was much different. And so it seems that Europa is responding to Jupiter's magnetic field. And how does it do that? Well, it's because it probably has a conductive material within it, liquid water, near the surface. A way to think about this is if you carry your keys through the airport metal detector goes off because your keys can conduct electricity. The metal detector is a big magnet, and you walk through it. So Europa is kind of moving through Jupiter's magnetic field and set off the metal detector, if you like, that the Galileo magnetometer measured. And so we know that it's conductive, and the iron core is too far away to explain the results. The best explanation is a liquid water ocean. And it's not that that's a total surprise, because there is a reason to think that Europa could have an ocean based on the geophysics, based on how Europa is deformed as it orbits around Jupiter. So as Europa goes around Jupiter, orbits around Jupiter, it gets a little closer and a little farther in its orbit. This is exaggerated, but just to make it clear. And when it's closer to Jupiter, it's stretched out more. And when it's farther away from Jupiter, it's not stretched out nearly as much. Jupiter is enormous gravity field, so it pulls on Europa. This animation is showing Europa orbiting Jupiter from Europa's perspective. So you're traveling along with Europa. And again, not to scale, it's exaggerated, but it looks like Europa's breathing, it's flexing, it's moving in and out, because when it's closest to Jupiter, it's stretched out, and when it's farther away, it contracts a bit. Well, that generates heat, all this flexing. And the heat is generated where the icy shell of Europa is softest down in its interior, warmest and therefore softest down in its interior. And that's enough heat to maintain an ocean within Europa below an ice shell something like 20-ish kilometers thick. That's about 13 miles thick. But again, that was just the theory, and then along comes the Galileo spacecraft and the magnetometer and says, look at that, there seems to be a conductor about 20 kilometers down below the surface of Europa. When we look at the geology, as the scientists who were here the last few days were talking about, Europa is covered with these bizarre ridges and grooves. So this is a double ridge, very typical of Europa's surface. And what is it, 20 years since we got this data? We still don't really understand how these ridges form. There are good ideas. There was probably a crack in Europa's surface ice, and all this flexing may cause the ice to move back and forth. And again, like rubbing your hands together, that generates heat. Well, warm ice that's heated, rises and may push up the surface above it. That's a model that I tend to believe. It doesn't mean it's the right model, and we need more data to really understand how these ridges form on Europa's surface and what they might be telling us about liquid water below. We also see these things, bands. Those ridges, by the way, they're typically a few kilometers across. So if you see a picture with a big ridge, that ridge is probably, 2 to 5 kilometers across. This band is more like 20 kilometers across. This feature snaking across the surface of Europa. You can see these hints of ridges within. You can also see that older features out here look like they were just broken by this band. Well, you can play a game of matching up the older features in Photoshop, like these two and these two, and putting them back together, and they match just exactly. Sorry, I don't have any of the reconstructed versions here, but I think you can picture it. Here's another one, this wedge-shaped band that just opened up on Europa's surface. This part we zoomed in on with Galileo. Louise and I and others at Brown University planned these images of Europa's surface back then. And Louise is really the person who has studied bands the most on Europa's surface and explained them as possibly like seafloor spreading on Earth. There are places on the Earth's ocean floors where new crust is made as the seafloor is pulled apart and new material moves up. And recently, I have a colleague, postdoc, working with me at JPL, who's been doing models. Sorry, Louise, just last night I replaced your beautiful sketch of how these bands work with Sam's model of how these bands may open up. So this is showing a cross-section, his model of cold, stiff ice here and warm, flowing ice below. The colors are kind of backwards of what you might imagine, but that's okay. And if we put the movie in motion, pulling on this ice causes rifting and stretching and warmer ice to rise up below and ultimately come out onto the surface. In this movie, it cuts off just a little too soon. And so we're starting to understand, all these years later, a bit of the specifics of how these bands may open up as Europa's crust is somehow pulled apart. Well, if there's all this pulling apart and making of bands, and where's the ocean come in? Well, the ocean's probably down there below that warm flowing ice. But what's interesting is that these bands can be places where ice that's now frozen again in the ice shell was in contact with liquid water and brings that watery material up to the surface. So these bands may be places to go look for whether there's evidence for life in the ocean because they're dredging up deep material to the surface. Let's see if I can make this go to the next one. Come on. So Louise, along with another researcher, just a couple of years ago, published a very nice paper on how do you compensate for all that pulling apart and making these bands? Well, there are some places, Louise and Simon Kaltenhorn believe, from reconstructing the surface, are places where cold ice is sinking down back into that warmer ice. So those who know Earth geology may know of subduction zones. There are big earthquakes at subduction zones, so we hear about them on the news the hard way. And something like that may be going on in Europa, and that's a model that continues to be tested. So again, the ocean is down here, not directly participating in that cool geology. There are some impact structures on Europa, as I mentioned. The smaller craters, this one about 10 kilometers across, kind of look like craters on the moon. But bigger craters like Puil or Mananin look very flat, like they formed in a warm icy shell, relatively warm, where the ice could flow and fill in the craters. And the two biggest impact structures are completely bizarre looking, like bullseyes, because the impact probably penetrated all the way through the ice shell to water, and that ice then flowed inward to the center and filled in the crater and made these concentric rings. So actually, the idea that the ice shell is probably about 20 kilometers across largely comes from these two big impact structures, where we'd say, well, it looks like from the measurements of the size of these that the ice shell was about 20 kilometers across, 20 kilometers deep, to make these impact sites about 40 kilometers across. Also, these things on Europa, the fancy name's lenticulae, that's just Latin for freckles. They're about 7 kilometers across, and they too probably have to do indirectly with an ocean, but more a reflection of what's going on in the ice shell. So I bet a lot of you remember lava lamps. Lisa, good. Someone's still got one. I got one in my office to remind me of convection in Europa. Because in a lava lamp, there's a light bulb here, and it warms the wax, and it rises up through the cooler oil, and then the wax cools off, and it sinks back down, or different density oil. And the same may be going on in Europa, where the tidal heating allows these blobs of warm ice to rise up to the surface and make these pits and spots, these lenticulae that we see. And this is a model by Amy Barr, who's a researcher now in Germany. And she's modeled, again, the ocean down here. It's warm, right? I need my cheat sheet of temperature conversion. About 260 Kelvin, minus 10 Celsius, about 8 degrees Fahrenheit. So that's the warm stuff. The cold stuff at the surface, about 100 Kelvin, about minus 170 Celsius, about minus 280 Fahrenheit. So this ice is really cold and stiff and hard, and this ice flows because it's warmer, but not nearly as quickly as it's shown here. It takes probably about 100,000 years for the ice to rise up from the bottom to near the top of the ice shell, and then it's pretty tough to figure out how to get it out of the ice shell. It probably has to crack, get that stuff out. There are also these regions of Europa called, aptly named, chaos, where the bright icy stuff, as we saw before, looks like it's kind of crumbled in place. There's some plates that have old ridges that look like they've tilted and foundered somewhat, and this looks a lot like Arctic sea ice. When this was first seen, it was thought, well, is this the ocean coming right to the surface, telling us there's water right there today? Or is it warmer ice that's come up to the surface and disrupted the surface in some way? And to give you a feel for the scale of this specific chaos region, you can see the ring road right around there. So this block's about 5 kilometers across. Yeah. One more very cool feature about Europa, there might be plumes. As you'll hear from Jonathan Lenine, he's talking about Enceladus. He's going to talk about the amazing plumes of Enceladus, where we know there's water shooting out of this moon of Saturn. Well, Europa, not to be upstaged, might have plumes, but Europa's being a bit secretive about it. Here, from a Hubble image, so viewed from orbit around Earth, we've seen glow of hydrogen and oxygen off of the edge, the limb of Europa. And it's thought that Europa might sporadically have a burst of water, a plume, like in this artist's conception, that then breaks down into hydrogen and oxygen and glows where the Hubble Space Telescope was able to see it. The problem is they're not consistent. They're right on the edge of detection. So there's a big program by the Hubble Space Telescope to keep searching for possible plumes at Europa. And why do we care so much? Because then you could fly a spacecraft right through one of these things and directly measure what the composition of the subsurface is, as Cassini has done at Enceladus. Oh, sorry. I didn't mean to have sound. Stop. That's the NOVA narration going. Whoops. Can we turn the sound down? I don't know how. My computer is not making it go down. It's cool, but it'll keep saying it over and over. That's I stopped the movie. So this is an example of a black smoker on Earth, as the narrator will tell you. Superheated over 7. It's a place on the Earth's ocean floor where water has seeped down through cracks at one of these, at a place where there is very hot rock in the subsurface, where warm rock has moved up to just below the surface of the ocean floor, and water seeps in there and then escapes just charged with chemical nutrients. That kind of environment is fantastic in supporting life very locally around these things that are called black smokers. And Europa may similarly have a hot rocky mantle. We don't know. If so, then water can seep down there and emerge charged with chemical nutrients that could potentially support microbes in the ocean of Europa. So what we really need to understand is what's the chemistry of Europa's surface, and what's that telling us about the chemistry of its ocean and whether that might be a habitable environment. Okay. So now it's not going to give me my words that I wanted to see. That's the one part I didn't test, was the sound. So Europa, and there are all the organisms swimming by. So Europa, in terms of the ingredients for life, probably has more water than all of Earth's oceans combined. As far as the essential elements for building molecules, probably from Europa's formation and from impacts, but we don't know yet because the Galileo mission didn't tell us enough about the composition of Europa's surface. We have some idea there are salts there, magnesium sulfate, and probably some other salts, but we don't know for sure, and we haven't detected organic materials yet on Europa's surface. We need to look more carefully with better instrumentation. The chemical energy in Europa, it might come from below in these black smokers, if they exist there, and it could come from above because radiation, charged particles hitting Europa's surface make oxygen-rich materials. And if those oxygen-rich materials can get into Europa's ocean, and if Europa has black smokers down below, then it can be a very favorable place for life in terms of chemical energy. As far as how long Europa's environment has been stable, probably for the age of the solar system, that's a bigger question that's going to be hard to address from our mission, but combined with other data sets like from the European JUICE mission, which is also going to the Jupiter system, we might get a feel for how old, let's see, how to put this, for how long this tidal heating has been going on at Europa. Okay. So what do we want to do with a mission in my last few minutes here? Overall, our goal is to explore Europa to investigate its potential habitability. Now, what does that really mean? That really means understanding its ocean and ice shell and the processes within, understanding Europa's composition, like these dark splotches, and try to understand what they're made of and whether that stuff's coming from the ocean, and understanding its geology, which tells us about how it got to be as it is and how long have those processes been going on. We also want to understand Europa at really high resolution. The best image of Europa's surface from the Galileo mission was at about 8 meters per pixel and somewhat oblique, and boy, is it a jumbled mess. We want to understand, are there smooth places where we could someday, hopefully not too long from now, put a lander down on Europa's surface based on the information from the Europa Clipper mission. This is our spacecraft as we understand it today. We're getting closer and closer to design. We are in phase B of the mission. For those here who that means something to, we're essentially in the design phase of the mission, and the spacecraft keeps maturing. We're a solar-powered spacecraft. There are 4.5 solar panels per wing here. Let me put some labels on here. There's our high-gain antenna. During the flyby, it's just pointed up away from Europa. This is magnetometer, boom. What else can I point out here? Our remote sensing instruments, cameras, spectrometers, are looking down during the flyby, and there are two mass spectrometers, one for dust and one for neutral gases, that are pointing in the direction we're flying. So this allows us to gather data from all the instruments simultaneously. That's something that the Cassini mission could not do, because the instruments kind of slapped all over the spacecraft. You could only use a couple of them during any flyby of Cassini at, say, Titan. But we don't have that time because there's an awful radiation environment at Europa that we're battling. So with every flyby, it's immersed in more radiation in the vicinity of Europa. We have an ice-penetrating radar that we built right into the solar, or are building, or going to build, right into the solar panels. 4 VHF antennas and 2 HF, high frequency, versus very high frequency antennas that will be used to plumb the ice shell to tell us where is there liquid water below the surface of Europa. I'll run through the instrument suite in total in just a minute here. So how are we going to accomplish this mission? We're not an orbiter. We were originally planning to go into orbit around Europa. That's really expensive because of the radiation environment, because then the parts that your spacecraft is built from and all the instruments have to be very radiation hardened, and that's very expensive. So we cut the proposed cost of the mission down about in half by instead being in orbit around Jupiter and making many, many flybys of Europa. So that's analogous to what Galileo did, but here we're concentrating just on Europa, getting about 45 flybys, and with modern instrumentation that is designed to understand Europa's habitability and look for water and look for organics and image the surface at super high resolution, things we were not able to do with Galileo. So this is the kind of thing. What? Oh! I missed my little story here. Right. So for the Trekkies in the crowd, I'd like to think of this as the Tholian web, essentially, that we're immersing Europa in a web of flybys like those Tholians did. So what's the science we want to do? We like to call it synergistic science, because really it's the sum total of all the instruments that get us what we want to know. Well, there's gravity. As Europa goes up and down, not to scale, it tugs on the spacecraft, and how it tugs on the spacecraft tells us about how much Europa is flexing. Now, from orbit, you can imagine this is easy to measure as you're flying around Europa, but from a flyby mission, we fly by when it's like that, and then later we fly by when it's like that, and putting that all together, we can understand how Europa is flexing as it's orbiting around Jupiter and be able to confirm an ocean. If there's an ocean, it'll be flexing by 30 meters every time Europa goes around Jupiter. Every 85 hours. That's 3.55 days. It flexes 30 meters. But if there's no ocean, it'll flex by 1 meter, and we will barely measure anything. But most likely, we think there's an ocean, and we'll be able to measure that. We want to measure the magnetic field around Europa to essentially, in some ways, repeat what Galileo did, but do it a lot better. With 45 flybys, we can measure, we can get out of the data not just whether there's an ocean down there like we did with Galileo, or we're pretty sure there's an ocean down there from Galileo, but instead we can get its thickness and how salty it is, how conductive that ocean is, much more precisely. And the plasma data measures the ions, the charged particle environment around Europa, which is needed to correct and understand that magnetometry signal. We'll be imaging, so instead of a bald surface, as this is illustrating, we'll be able to understand what's going on in detail. We'll get the whole moon at about 100 meters per pixel or better, and we'll get spots up to a ½ meter per pixel. We'll use infrared spectroscopy to understand what the chemical signature of the surface is like. Where are there organic materials? Where are there salts? What kind of salts? What kind of organic and other materials? We have a thermal imager to look for hot spots. as Jonathan Lunine will tell you about it, Enceladus, we can see Enceladus is warm enough that it essentially glows in the long wavelength infrared, because it's so much warmer than it should be. Not that it's hot. I said it's 100 degrees Kelvin. So a hot spot might be 150 Kelvin, something like that. But that's warm for Europa. And that's the kind of thing we've seen at Enceladus. And then with the ice penetrating radar, we can understand what the subsurface plumbing is like. We could find lakes below the surface. And that's the most popular model now for how that chaotic terrain forms, by collapse into a subsurface pocket of water at Europa. We'll be able to tell if that ice shell is really convecting down there. In the ultraviolet, we can look for the glow that might be associated with plumes, places where Europa is leaking material into its very, very thin atmosphere. And then finally, through spectroscopy, mass spectroscopy, we can get at the dust and the gas, as I mentioned. Hard to tell, a little dust and gas appeared there, around Europa, to get at the detailed composition of what might be leaking out in terms of the gas, or what might be blasted off the surface in terms of the dust. So all these instruments work together, and my vision of what I would love to see from Europa would be to find some sort of oasis, like this is trying to illustrate here, a region where there's liquid water, there are organics, there's warmth, and that's the kind of place where we would want to send a future lander. So I'm a little late on time. Do I have a few minutes to show this cool animation? Okay. Oh yeah, light's not too bad, thank you. So this is a cool animation now that you know our instruments. You'll see down here is illustrating where Europa is in its orbit, and here's the Europa Clipper coming along to intersect Europa. The Earth and Sun are out that way, so here are our solar panels charging up for an encounter. Not in real time. And now the spacecraft is turning to be able to do some ultraviolet scans of Europa. There is a key to the code of our instruments over the bottom left, and the purple is the ultraviolet. I'm going to come over here so I can read it as this is going on. You'll see a couple of flashes of blue. That's the narrow angle camera. That orange was a calibration of the thermal instrument. Spacecraft turns into an orientation where it can scan across. Oh, I see. It's doing a thermal observation. There it's doing an infrared observation. And here it's doing a scan across the surface with multiple instruments at the same time. As we pull in, doing some of that infrared spectroscopy, the thermal instruments just going all the time, integrating to measure the temperatures. More flashes of narrow angle and the wide angle camera, which covers much of, or all of Europa there. The solar panels swing around to an orientation where the radar can do its job as we fly by, and all instruments go on at once below 1,000 kilometers, picking up more data than the typical avionics could handle, as we've now learned in putting our spacecraft together. And we've had to go to a more primitive avionics system than we were hoping, just because it's so hard to gather so much data at such a high speed during our flybys. And then we rinse and repeat, or do it backwards as we fly out. There's that joint scan again. So we want to have very simple, repeatable observation types is the goal here. And this is something that the scientists on the mission, about 135 people, have been negotiating through the principal investigators, for the most part, the 9 people who are in charge of each of the instruments. One principal investigator per instrument. So, one last note, or penultimate note, how do we get there? We could, the earliest we can launch is about May 2022, And if we launch on a conventional rocket, an Atlas, Delta IV, or Falcon Heavy, then we have to go in toward the inner solar system, do a couple of Earth flybys, do a Venus flyby to allow those gravity assists to get us out to Jupiter. And it will take 7.5 years to get there, and it'll be 2030 by then. It'll be much better if we get to go on the Space Launch System that NASA is developing, which has the launch capability to send us on a direct trajectory to Jupiter in less than 3 years. And then I won't be retired. Yeah, can see this mission to fruition. Thinking beyond that, though, is the idea of a lander. We looked at whether we could attach one to this mission, but that would be too expensive and too massive. So JPL and NASA are looking into whether we could send a separate mission that would land on Europa with the goals of searching for evidence of life, for assessing the habitability of Europa from the ground, and characterizing the surface and subsurface to enable yet more distant future exploration. And with that, here's our website for future reference. Damn bums. Thank you very much.
Okay, so we'll take some time for questions now. So please raise your hand, and we will bring a mic to you, as there's folks here want to hear, maybe in the overflow that want to hear, as well as those who are on the line. So we'll start right over there.
How big is Europa?
Oh, I'm sorry, I didn't say. It's about the size of Earth's moon.
The size of Earth's moon?
Yes.
Okay. How far is it away from Jupiter?
Boy, do I know the numbers. I don't know the numbers, but
Approximate.
I think I think the Earth's moon scale, that system would fit between Io and Europa somewhere. So I have to look up the number. I don't remember off the top of my head. I really don't. But a bit farther than the Earth moon distance.
How far away was the Clipper from?
Oh, yeah. So our flybys would be from 100 to about 25 kilometers off the deck
That close.
of Europa.
And the gravity doesn't pull the Clipper.
Not a big issue. I mean, that's
Wow.
factored in. With Cassini flying by Enceladus, we've done it to 25 kilometers several times.
Thank you.
Yeah, is there any evidence of islands or mountaintops on Europa poking through the ice?
There is not any direct evidence for topography poking above or into the ice shell, and that's consistent with the H2O layer probably being close to 100 kilometers thick. So the ice shell doesn't seem to be grounded, but we could be surprised. Well, actually, there's a lot of geological evidence that says the ice shell. Can I make him stop the flag? There's a lot of evidence that suggests that the ice shell has actually moved relative to the interior, and that might help in making those cracks. So I talked about the tidal flexing, but there's also the idea that the whole ice shell moves relative to the interior. So that would be really hard if it were grounded, but much easier if there's a global ocean.
What is the value of Europa's gravity compared to Earth's gravity?
Oh, again, so I don't have all the numbers memorized. Let me see. So Moon's gravity is what, a sixth. So Europa is about a seventh, if I remember right, of Earth's gravity.
Real quick,
yeah, lunar light, moonlight.
are there any questions from the overflow?
There are no questions from the overflow. Thank you.
I'm relying on these folks.
What's the composition of the atmosphere?
Oh, so very thin atmosphere, a picobar that is 10 to the minus 12 of of Earth's atmosphere, it's mostly H2O and O and in the atmosphere. Yeah. because it's stuff that's knocked off of the surface of Europa, and the hydrogen is mostly going to fly right away, and that leaves H2O and O sitting around at Europa.
Have you been able to identify any difference in thickness of the ice shelf, say up at the poles versus an equator?
Good point. Sorry, I just remembered. And OH, I should say, because H2O breaks apart. OH. So it's expected that the ice shell at the poles should be thicker because it's colder. And that's actually why we think that Europa might flip over every once in a while, because the ice shell is thicker and that wants to be at the equator. And so that would predict that it flips over and then it thickens again and it flips over again. We don't have direct evidence in terms of the geology for that. For the thickness differences. There is some evidence that Europa has actually flipped over and moved around. But that's something that hopefully we can test with the radar. If it can penetrate all the way through the ice shell, or even the magnetometry can get us an idea of the thickness of the ice shell. But radar would be best for looking for variations in thickness. But it's not just pole to equator. This tidal flexing, but the heat it creates predicts that there should be thickness variations around the equator too, because different parts of Europa are flexed differently as this is going on. Right? It's not flexed a lot at the places pointing to and from Jupiter. It's flexed a lot some distance away from those points, and that translates to heat, and that translates to thickness variations, we think.
Yeah, I actually had a question about observing the ocean, but I forget that. I mean, this flipping thing. Are you talking about? Are you talking about the icy crust flipping, or the entire core ocean, everything, and what would that do to the planet's axis? And...
Right. The icy. I'll go back to this picture. So the icy crust above the rocky mantle. So this doesn't happen to the moon, our moon, because there are density differences that lock the moon in place facing toward Earth. But and so that's probably true of the interior of Europa. It's probably locked facing Jupiter. But the ice shell is allowed to slip. And there are some forces, some torques that, well, there are various mechanisms that can allow it to slip. So yeah, we're talking about the ice shell moving above the interior.
Can you indulge me and let me ask my original question now?
Sure.
So,
if others do.
And I know this is way out there since the lander has been disposed of for the time being, but exploring the subsurface ocean, what are you looking at? Because you got to drill through a ton of ice, and then you're not going to have any light source if you have some sort of submarine vehicle. What's right? What are you talking about there?
That would.
Oh, there's the whole issue of the drill hole freezing back up.
Yes. So yes, it would be an enormous challenge to try to get into Europa's ocean. I think it would be a much more reasonable challenge to try to get into a pocket of liquid water if we find such with the Clipper. Because I wouldn't want to try to melt through 20 kilometers, but maybe through 3 kilometers into a lake. Now, would a subsurface lake be an interesting place to look for life? I think we don't know yet, really, in terms of what's the chemistry like in there. Would there be the energy that could support life in such a lake? This came up in our workshop, and people were like, "Oh, yeah, huh." To think about that, because no one's really thought about it yet. So, in terms of technical challenges, yes, it's an enormous technical challenge. They just had a workshop. Louise was there, though I wasn't, about how we could drill in. My postdoc was there, whose ridge picture I showed, or band picture, and he said he came away from there saying, this is something we could actually do. Do you have the same impression that it's not so impossible as we might think?
Yeah, I was also quite encouraged. I think the big problem actually is just getting down to the ice and getting your drilling rig situated. But actually, I was more encouraged about being able to drill through the ice once you're on it or in it. because you can melt through ice. You can't easily melt through rock, but the actual material makes it a little bit easier once you're there. The problem is that right now in the Antarctic, if you want to drill, they have these kind of wagon trains of material that they take down there, and multiple people, and they go for weeks at a time. And if we can get our material to Europa and miniaturize our drilling equipment, I think and actually get into the ice. The starting problem is the hard part. Once you're in the ice, I think I'm more encouraged that yes, you probably could get through a few kilometers without a huge amount of technological advancement, and actually do it. I think we can figure out how to do that. Yeah, it's an interesting problem.
I forgot Sam is here. He's just gave a big thumbs up
Oh, yeah.
because
He's still here?
he
Awesome.
thinks, yeah,
Did you agree with that, Sam?
we can get through.
Want the mic? Sorry, I know. Sorry, tell us if you need.
No, this is wild. Go ahead.
Just talking about
So the really encouraging thing about drilling through Europa's ice shelf is that we possess these nuclear batteries where we harness their heat energy to turn it to electricity in space. And if we bury these to melt the ice, you've made a race car without brakes. You can't turn nuclear heat off, this radioisotope heating. And so if you can get the thing started, you can't actually stop it. And so the challenge, like Louise said, is you got to be in the right position with equipment to handle the journey down. But the major problem isn't how do you keep going down, because that's going to happen once you start. It's how do you get the whole project started.
Real quick, anything overflow?
I just wanted to ask about the best idea for the color of the stripes. Is that still Tholin's?
The reddish stuff, you mean?
Yeah.
Yeah, I sort of skipped through that, but I'm going to go, if I can take a moment to go back to my little inset picture that had that. So from Galileo, we look at the fingerprints of the light that's reflected off the surface. So this is showing wavelength, and this is showing how much light is reflected off as a function of wavelength. And ice has very particular shape of this curve. And when we look at this reddish stuff, it has a different shape that tells us that there's probably magnesium sulfate salts and probably battery acid. So it might be Epsom salts or it might be battery acid down there. What's probably true is a combination, that the Epsom salts, the magnesium sulfate, is probably, we think, coming from deep down in the ocean, whereas the battery acid is made at the surface by radiation coming in and breaking molecules apart and letting them recombine. But again, it's still somewhat speculation. We're going to have incredible spectral and spatial resolution from the Clipper spacecraft to try to get at the nature of those particular salts. And hopefully organic. They're there.
Okay, how does the pressure at the bottom of the ocean on Europa compare to the pressure at the bottom of the ocean on Earth?
So the pressure at the deepest part of the ocean floor of the Earth, the Marianas Trench, is about the same as the pressure at the bottom of Europa's ocean at the ocean floor of Europa. So we know life can exist under the pressure of the deepest parts of Earth's seafloor. So pressure doesn't seem to be a limiting factor in allowing for life at Europa.
Since you've been, if I understood your schematic, the Clipper will be between Jupiter and Europa. So what sort of instrument are you going to turn the same instruments onto Jupiter that you're doing into Europa?
Good question that the scientists have been asking too. So to ensure that the costs are manageable on this mission, the instructions from NASA are we're looking just at Europa. Now, what a lot of the scientists hope is that once we build the spacecraft and looking at other places, it's driving the cost, then hopefully we can look over to Jupiter. We're certainly going to do some calibration at Ganymede, like test out instruments, although the Ganymede flybys are in the dark. But we can still use radar and test them out and other instruments. So we actually fly on both sides of Europa. So sometimes we're between Europa and Jupiter, and sometimes we're just on this side of Europa. And the only observations we currently have planned are Europa in front of Jupiter to look for evidence of plumes that may be on the limb of Europa. That's one of the techniques that Hubble used to detect possible plumes at Europa.
We'll take one more question.
How many flybys and how long would the mission last for?
Oh, so right now we're planning about 45 flybys, and that may change as the give or take. And the whole mission, 3.5 years for the nominal mission, those 45 flybys. But a year and a half of that is big, long looping orbits at first to get into the resonance where we encounter Europa every 2 weeks. So every 4 times that Europa comes around, here comes the Europa Clipper to meet it. And the Galileo mission lasted 3 times its design lifetime. So maybe we'll get another 5-ish years out of it, I hope. Yeah, exactly. So we're hoping we'd have an extended mission that would allow us to focus down on specific things we find. If we find plumes, that would be a great opportunity to fly through them.
All right, well, let's thank our speaker one more time.
Thank you.
So we'll see you back here in January or December 2nd. But until then, go ahead and join us in the while we have a reception. Those of you watching us online, thank you very much.